In this class, we're going to talk about parametric linear programming. An approach to sensitivity analysis is to vary one or more parameters continuously over some intervals to see when the optimal solution changes. For example, in this linear programming problem, if we set B2 bar to be 12 plus theta and vary theta continuously from 0 to 12, in a similar way as discussed before, we can investigate the effect on the optimal solution of varying several parameters simultaneously. When we vary just the bi parameters, we express the new value bi in terms of the original value bi as follows. This bi bar is equal to bi plus alpha I times theta. Here, the alpha I values are input constants specifying the desired rate of increase of the corresponding right-hand side as theta is increased. For example, suppose that it is possible to shift some of the production of a current product from product 2 to product 3, thereby increasing B2 by decreasing B3. Also, suppose that B3 increases twice as fast as B2. Then we have B2 bar equals 12 plus theta, B3 bar equals 18 minus 2 theta, while theta is the rate of increasing B2. And then in this case, we can calculate by the formula earlier, Z star, which is 36 minus 1/2 theta. This is our new objective function. And then on the other hand, our B star will be S star, the matrix of slack variables times B bar, and then we can obtain its expression. So in this case, we can see that as long as theta is less than or equal to 2, the optimal solution is still optimal. The approach to varying several Cj parameters simultaneously is similar. In this case, we express the new value Cj bar in terms of the original values of Cj as Cj bar equals Cj plus alpha j times theta, similarly as the Bj's. Here the alpha j are input constants specifying the desired rate of increase of Cj as theta is increased. To illustrate, reconsider the sensitivity analysis of C1 and C2 for example 1 in our section 6.1. In this example, suppose that we consider both C1 and C2 changes by setting C1 bar equals 3 plus theta and C2 bar equals 5 minus 2 theta. Here the value of theta measures the fraction of the maximum possible change that is made. So we have Z, the objective function, will be the new C plus 3 plus theta x1 plus 5 minus 2 theta x2. So the optimization now can be performed for any desired fixed value of theta between 0 and 1. We shall now present the algorithm procedure. First, we consider systematic changes in the Cj parameters. For the case where the Cj parameters are being changed, the objective function of the ordinary linear programming model of Z, the objective function, equals the sum of Cj xj is replaced by a function Z theta, which is now the new coefficients are replaced by Cj plus alpha j theta, and then the variables are unchanged. While these alpha j are given input constants representing the relative rates at which the coefficients are to be changed. Therefore, gradually increasing theta from 0 changes the coefficients at these relative rates. The values assigned to the alpha j may represent interesting simultaneous change of the Cj for systematic sensitivity analysis of the effect of increasing the magnitude of these changes. They may also be based on how the coefficients would change together with respect to some factor measured by theta. For example, the unit profits. This factor might be uncontrollable, for example, the state of the economy, However, it may also be under the control of the decision maker, such as the amount of personnel or equipment to shift from some of the activities to another. For any given value of theta, the optimal solution of the corresponding linear programming problem can be obtained by the simplex method. To illustrate, suppose that alpha 1 equals 2 and alpha 2 equals -1 for this problem. Then we have our objective function z equals 3 plus 2 theta x1 plus 5 minus theta x2. So now we consider the simplex tableau for our problem. So this is our original final simplex tableau when we reach the optimal solution. Now the problem is that we have changed our objective function from old 3x1 plus 5x2 to this extra 2 theta x1 and minus theta x2. So in this case, in our final simplex tableau, we have theta for 0. Then our equation 0, the objective function, is z plus these non-basic variables x4, x5 equals 36. Now, if we actually introduce the value of theta, then in the simplex tableau, we actually have one more term of 2 theta x1 and then one more term of negative theta x2. Of course, first, they are on the right-hand side. So we move all the variables to the left-hand side and change our new objective function to z minus negative 2 theta x1 plus theta x2 plus the rest as before. So this is very similar as we as we change the coefficients of the parameters of the non-basic basic variables as we saw in the earlier class. So now we say that we're going to change the coefficients of the objective function in x1, x2 to negative 2 theta and theta. So this is our new simplex tableau. By looking at this simplex tableau, we first say that because x1, x2 are our basic variables, their corresponding columns are supposed to be unit. So before we actually apply the simplex method or do any of the optimality tests, we need to eliminate these two extra coefficients here. So we do Gaussian elimination to make these two columns in the proper form. And then after we do the Gaussian elimination, we'll get a tableau of this form. So in this tableau, we can see that x1, x2, x3 are the basic variables, and their corresponding columns are in the proper form. So if we simply look at this tableau, we can see that if we want to check whether this satisfies the optimality test, the only thing here is that theta is non-negative, so this value must be positive. However, we have this 9 minus 7 theta over 6. So as theta varies, this value may be negative or positive. So in order this solution still remain optimal, we just need this value to be bigger than or equal to 0. After solving the inequality, we say this table is optimal when the value of theta is between 0 and 9/7. At this point, as theta varies, our objective function takes the value of 36 minus 2 theta. That means as theta increases, our objective function actually is decreasing. So this is basically roughly how our objective function performs when theta is in this interval, and then the decreasing rate is -2. Next, we say if theta is bigger than 9/7, then this value in the equation 0 is negative. So then we say this is our pivot column. We do the minimum ratio test and figure out that in this case, x3 is our leaving basic variable. So repeat the same procedure in the Gaussian elimination to make this column proper, and then x4 is the entering basic variable. After we compute the new simplex tableau, we can see that in this case, since theta is bigger than 9/7, in our new table, this value is positive. However, on the other hand, we have this 5 minus theta over 2. As theta varies, this value can be positive or negative. So we solve inequalities and say that as long as theta is less than or equal to 5, this value will stay non-negative. So then at this point, all the coefficients in equation 0 are non-negative, so it passed optimality test. This table is optimal, and at this point, our objective function is measured by 27 plus 5 theta. So as theta increases, our objective function also increases at a rate of 5. So it's roughly like an increasing straight line. On the other hand, the discussion continues. If theta is bigger than 5, then this value in the equation 0 is negative. So we need to apply the simplex method again. First, do the minimum ratio test, find out the leaving basic variable, and then make the corresponding column proper, so x5 is entering and then x2 is leaving, and do the Gaussian elimination to make this column unit. After doing that, we can see that in equation 0 in this final tableau, even though it contains a negative value, but because theta is bigger than 5, this is positive. And then theta is non-negative, so all the values in equation 0 are non-negative. So this table is always optimal. So now theta is bigger than 5, we obtain an optimal solution. And under this condition, we can see that in this case, our objective function again is expressed in terms of theta. As theta increases, our objective function also increases 12 plus 8 theta. So at this point, we obtain, no matter how theta increases, this is always our objective function, and then we can roughly draw its picture. In this example, we also see that z star, which is actually a function of theta, the objective function value for the optimal solution changes as theta increases, as we saw earlier. In fact, the corresponding optimal solution changes as theta increases, just as the value of theta, while the slope of the z star theta function changes. These 3 different solutions are optimal for different values of theta. The first is when theta is between the interval from 0 to 9/7. The second is theta in the interval 9/7 to 5. And the third is when theta is bigger than or equal to 5. Because the value of each x3 remains the same within each of these intervals for theta, the value of z star theta varies with theta only. So to summarize the procedure for parametric programming, we say that step 1, we solve the problem with theta equals 0 by the simplex method as usual. And step 2, use the sensitivity analysis procedure as we saw in section 6.6.1, case 2 and 3, to introduce the change delta Cj as alpha j theta into our equation 0. Step 3, increase theta until one of the non-basic variables has its coefficient in equation 0 go negative, or until theta has been increased as far as desired. Step 4, use this variable as the entering basic variable for iteration of the simplex method to find the new optimal solution, and then return to step 3.